Okay, so we're starting to part 2 here. So draw 2 separate waves, one long wavelength, the other with a short wavelength. Indicate long and slow wavelength. Okay, what is this? C is the speed of light. The funny looking V is your frequency. Your lambda is your wavelength. Okay, H is Planck's constant. Okay, so you guys should be able to solve these problems given the formulas that you have. Okay, what is a photon? The best way to describe a photon is it's a packet of energy. It's what it is. We get bombarded by photons all the time. Okay, so when we go and solve a problem like this formula here, the energy of the photon is equal to Planck's constant times the frequency, which is also equal to Planck's constant times the speed of light divided by the wavelength. So we have an idea, okay? So it's not a question so much of how much energy does that one photon have. What happens when you have lots and lots and lots of photons hitting? Okay, so you have a bunch of problems there. Okay, chapter 5, we talked about the idea of the periodic table. Okay, Mendeleev, you should know him. Lustrous, malleable, ductile. Okay, you guys should know alkali, metals, halogens. Okay, you should know those things. Okay, metalloids, yep, that's fair. Okay, when metals become cations, do they become larger or smaller in size? Remember, if an atom loses an electron, it becomes a cation, not cation, cation. Okay, and it becomes smaller in size. Well, what's making the size? It's the electron cloud, the region where the electrons would be bouncing around in. That's what's happening. So when atoms pick up electrons, they get bigger. When atoms lose electrons, they get smaller. That's how it works. Okay? Ionization energy, what is that? Okay, remember how much energy does it take to rip an electron out of an atom? Okay, should know what the trend is, atomic radius. All right, so you should be able to tell about that. Electron affinity, electronegativity, talked about that. Okay, chapter 6, why is it atoms are formed in bonds? Gain stability and lower that energy. Okay, that's a key thing here. Now keep in mind, when the atoms bond, they want to have enough electrons to be like the noble gases. So when you look at fluorine, fluorine has an atomic number of 9. Neon has an atomic number of 10. Fluorine has 1, 2, 3, 4, 5, 6, 7 electrons in its outer layer, right? What's the magic number? Magic number is 8. So fluorine picks up that electron, right? So now it's picked up the electron. It wants to be like neon in that it has its full thing of electrons, but it's not going to be neon because it's fluorine, and it's fluorine with a -1 charge. That's like if Mr. Canu went and bought a Lakers outfit, the official Laker player outfit, put on the jersey, put on the shorts, put on the socks, you know, and all that stuff, get tricked out with the best shoes that the players get. Okay, it doesn't matter. I want to be like an LA Laker player, but I'm not going to be an LA Laker player. It's like fluorine's not going to be neon. It's not happening. It's got all the electrons in there, and it's got a -1 charge. It's kind of like Mr. Canu. I got all the stuff to be an LA Laker, but let's face it, I stink in basketball. I'm king airball, took a brick. All right, let's move on. The funny little symbols that you see there, keep in mind, partial charges, okay? Partial charges, about that. So we talked about the idea of Lewis dot diagrams as well, electrostatic force. Lewis dot diagrams, you should be comfortable with this. Electron C theory, you should be able to know lots of extra electrons floating around in the metal, it makes a difference. Okay? All right, let's go with chapter 7 because we didn't really spend that much on there. So in chapter 7, we're looking at the bonding with the atoms. We're looking at the theory, okay? How those molecular orbitals, that they kind of alter themselves. They change a little bit. And that's where you got sigma and pi bonds. Sigma bonds are always formed directly between two atoms. The pi bonds are above and below the two atoms, okay? And so pi bonds are involving the p orbitals. The sigma bonds are involving the s orbitals, okay? So which is actually stronger, sigma or pi? It's the sigma that's stronger, okay? So when we look at any time, when we look at something like this, there's only the sigma, one sigma there, nothing else. If you have a double bond, you have one sigma and one pi. Sigma will always exist in every bond that's out there, always, always, always. And then here, one sigma, two pi, like that. Okay? That's what's happening. Take a look. And again, I'll upload this to YouTube. Okay, resonance. Okay, well, what is that exactly? You have here are three little structures, and they're all correct for SO3. Okay? The thing is, which one is it? The correct answer is they all are. The real SO3 is a hybrid of the three of them. That double bond exists for all of it, for all those oxygen bonded with the sulfur. So it's a hybrid. Okay? Now, let's spend a little time here on shapes, shall we? Come on. Okay. So when we look at molecular shapes, really what's happening is the bonds and the electrons are making the difference. Okay? So the idea is this. Whenever you've got two atoms together, that's it. It is automatically linear. Okay? Always, 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 always. If you have three, okay, so here's three atoms. This one is going to be linear, but are they always going to be linear? No, because you can have something that is bent. So here's an example. It's not cute, it's O. Let's see. Yeah. So that's an example of bent. What makes it bent compared to this? See these unshared electron pairs? That's what's forcing it down. That valence shell electron pair repulsion theory, VSEPR. That's what's happening. And that's why we're seeing that, okay? When we look at something that is flat like this, this is pyramidal. Here it's pyramidal, okay? But what about tetrahedral? Tetrahedral, you have something on the four corners. You have an atom that's attached to the four corners like CH4. That's tetrahedral, ladies and gentlemen. The trigonal planar we already have. Okay, oh gosh, I screwed up. This is not pyramidal. I'm so sorry, guys, I'm not awake. This is trigonal planar. Let me erase. This is trigonal planar right here. It's a flat triangle. If I turn this, it's going to be flat. Pyramidal, what does that look like? Okay. Pyramidal, oh, come on. All right. When we look at something like pyramidal, so if we have N here, and we have 3 H's, normally it would be a trigonal planar, it would be flat, except for this one pair of electrons. That's what makes it a pyramid. That's what makes it a pyramid, guys. It's this, okay? So pay attention to that. All right, I'm going to move on. Because polar versus non-polar, okay? And then I got to wrap up. I really need to wrap up here. Polar versus non-polar. Okay. Polar versus non-polar. This is something that you guys should know. When we look at a polar molecule versus a non-polar molecule. So when we look at something like CO, like this is non-polar. There's no, it's completely symmetrical. There's no asymmetry involved in this. On the other hand, when we look at something like this, on the other hand, this is quite polar. Why is it polar? It's not symmetrical, it's asymmetrical, okay? In other words, when we're saying that something is symmetrical, that means when you go around it, it should be having the same charges all the way through. There's no exposed electrons here. Here you've got exposed electrons, electron pairs. Here you got the positive end. That's where those partial charges come in. And here you got the partial negative charges coming in. That's what makes this polar, okay? So when you have something like CH4, is this polar or non-polar? It's non-polar because there is no area of negative. It's all partial positives here, right? So that's something for you guys to think about. Okay? Now, I am not lucky today, am I? All right, let's try this. Thank you. Okay, so no, C2 isn't. But what about our flat triangle? What about our trigonal planar? Is that polar or non-polar? It's non-polar because everything is partial negative, partial negative, partial negative. There is no partial positive anywhere in there. Now, if I went and did this, is it polar or non-polar? Now it's polar. Why? This is making it asymmetrical. Now it's polar. Just simply changing one thing. So here, if I change this to an H, guess what? This is now a polar molecule. Okay, that should be it, guys. I hope this will help you guys out. And like I said, I'm going to put it up on YouTube. All right? Peace out, yo.